All right, we're going to take just a minute to try to figure out navigation and bearing in the real world and show you sort of how that ties into what we're doing with trigonometry in class. So I put navigation and such because there's like a few components to this. So the first thing to understand is, you know, your compass, north, south, west, east. Hopefully we all know our directions that way. But whenever you're describing where a location is, you have several ways of doing it. So I'm going to draw a random line or vector. We're going to be calling them vectors pretty soon. Whenever you look at where that's located, you know, you might say, well, that's in the northwest, and you're correct, but you need to be more accurate than that. You either need to tell somebody the exact angle from the west or the exact angle from the north, or we can give bearing. Okay, so the first thing I'm going to do is take a look at this and say, well, maybe, what if this was like 55 degrees? Okay, so if I wanted to write this out, I have three options. I could either say that red line segment or vector is 55 degrees north of west. Hopefully that makes sense because you're going northerly direction from the west. So you start here and then you move up 55 degrees. You might also see it written this way. Ooh. West, 55 degrees north. So if you see it like this, the letter in the front is telling you where to start. So it's saying, hey, start in the west and then go 55 degrees north of that. So these both are acceptable ways of doing it. And then true bearing in the real world, everybody, you start in the north. Okay, I know when we did unit circle, we would start in the east and we'd go counterclockwise to measure. But in the real world, you start in the north and you go clockwise. And that amount, that angle that you travel would be your actual bearing. So if you don't want to have to use any words like north, south, east, or west, you would just say a bearing of, and you'd have to give that full angle, which in this case would be 300 and, is that 305 degrees? Let's see, 55. It's actually going to be, oops, let me erase real quick. It's actually going to be, this whole part here is worth 270, and then I'm going to add 55 to that, right? So the total there would be 325 degrees. So if I said a bearing of 325 degrees, that would count for exactly where this is located as well. Okay, so now that you know sort of how to measure, there's another thing that might come into play, and that is instead of doing an angle with a decimal, you will sometimes see an angle written in terms of degrees, minutes, and seconds. Okay? Degrees, minutes, and seconds. And so angles are sort of measured almost, you could think of it almost like a clock. I know that's what it feels like with minutes and seconds, but it kind of works the same. You could think of the degree as the whole hour, and you should know that there are 60 minutes in 1 degree, and there are 60 seconds in 1 minute. So in an entire degree, there are actually 3,600 seconds. And the reason that's important is because if you wanted to actually compute where something was, like if somebody said, oh, okay, that boat is traveling at 21 degrees, 33 minutes, and 2 seconds. And by the way, as I said it, I wrote it, but that's the notation. 1 tick mark here is for minutes and 2 is for seconds. This would equate to a decimal that can be found by treating the 21 as the whole number and then adding to it these fractions of time of an angle. Or I think of it as time, that's why I said time. So 33 minutes, you would actually think of it as 33 over 60. Because that's how many minutes are in a whole degree. And then 2 seconds, you could do that. Now, that would be how you convert. And so when you type that all in the calculator, you'll get the decimal. Another way that you can do it, there's actually a fancy button on the calculator that says DMS, and that stands for degrees, minutes, seconds. And so what that'll do is that will take a decimal for you and turn it into the degrees, the minutes, and the seconds. Let me tell you what screen that's on so that you can play around. Let's see. If you hit Second Apps on your TI-84, you're going to have a list of things. You'll see a degree symbol, you'll see a tick mark, and somewhere down there you'll see the DMS. So you're going to use these if you're wanting to type in quickly, like if it was, you know, 2 degrees and 41 seconds. You could just type that in just like that using your calculator, and it would tell you the decimal that it equates to. And I'll type that in just a second so you can see. You're going to use this one if we're working backwards. So like, let's say I gave you 7.632. If you type in that decimal and then right behind it, if you do DMS and you hit enter, then that's going to give you the degrees, the minutes, and the seconds. So let's grab a calculator, type in both, and see if you're doing that right. Voila, the magic of technology. So I've already typed them in and entered them. You can hit pause if you haven't had a chance, but this is what your calculator should be reading out if you have typed these in correctly. And like I said, that's all found under Second Apps on your calculator. Alright, so why would we need to do this? Well, because if you're solving a problem, sometimes the picture may be drawn in that way. And I'm going to give you a fat word problem here that's going to kind of incorporate all this, and we'll show you how to get out of it. Alright, so here's your word problem. Okay, so this is a doozy. This is a little bit of every single thing I can think of with bearing, direction, and velocity all in one problem and how you could be asked to solve. So I'm going to sketch this as I'm reading it out loud to you, and then we'll go from there. All right, we always want to start with our north, south, east, west. Okay. Plane A flies from Chicago. We're going to call the origin Chicago, okay? Plane A flies from Chicago around 2 p.m. at a bearing of 51 degrees. All right, so if it just says bearing of 51 degrees, that means we're going to start in the north and we're going to go 51 degrees clockwise from that. So right over here in green is going to be my plane A, okay, my airplane A. All right, and then another plane B leaves Chicago at the same time, and it is headed south 20 degrees 5 minutes east. So this means I'm going to go to blue here. Start in the south, and we're going to go 20-point-something degrees, 20-point-something degrees to the east of that. So 20-point-something to the east. All right, so this is plane B. So notice I started in the south, and then I just headed to the east. All right, now I'm not going to label that. Well, I can label that as 20 degrees in 5 minutes, but it's so much easier to calculate these things whenever they're in decimals instead of degrees and minutes. So I'm going to go ahead to my calculator right now, and I'm going to type in 20 degrees and 5 minutes and see what that's equal to. You could also just type in 20 plus 5 over 60, because that's the math that the calculator is doing since it's minutes. All right, so I'm getting 20.083, and that's what I'm going to call that, 20.083. All right, now, these planes are traveling at these angles, but they're traveling for a certain amount of time and at different velocities. So this is where a little bit of, speed and distance equals rate times time stuff comes in, but it's not going to be that hard, guys. All you have to do is look at the time that's lapsed. So like they leave at 2, they arrive at 4, right? Or not arrive, but we're trying to see how far apart they are at 4. 2 hours have passed. And if plane A is going 400 miles an hour, but he does that for 2 hours, then how far has he gone? Well, 400 times 2 hours is 800. That is the velocity or the length of this green line that I drew. I'm just going to call that the length of that. You'll learn when we do a chapter on vectors why. But not today. Today, just trust me and label it. All right, the next one. How fast was B going? Okay, B is going 421 for the same 2 hours. And so that's going to be 842 if I did my math correctly. And so that's what I'm going to label this blue line in terms of the length. So we're going to call that 800 long. This is 842 long. And the question is wanting to know how far apart these guys are. You know what I'm saying? So how do I do that? Well, how do I do that? Okay, that's what we want. We want to know how far apart they are. So you formed a little triangle. I've got two sides, and I don't have anything over here. So our best bet is to try to go for this angle that's in here. I'm going to kind of color it in, because if you can find that, we will have an SAS triangle, and then you can do law of, what would that be? Cosines. Alright, well, how do I find that angle? Easy peasy. You got a straight line. We all know a straight line is worth 180. So right now I'm typing in 180 minus 51 minus 20.083. And I'm getting 108.1. Come on, pen, work. I'm getting 108.917 degrees. So I'm going to roll out into a big fat law of cosines right now. 800 plus 842 squared minus 2 times 800 times 842 times the cosine of 108.197. Going to type all of that in at the same time, and then afterwards I'm going to square root whatever that is, and then you'll have the distance between them. So everybody shut up and type on your calculators. I'll do the same. And let's erase. Ready, go. 800 squared plus 842 squared minus 2 times 800 times, what was that, 842? Ah, dang it, I messed up. Y'all are going to beat me. Maybe not. Let's see. See if I can make up some time. Cosine of 108.917. Okay, I'm getting, after all is said and done, 1425.62, and that would be miles. That's how far apart they are. So that's a big fat problem that kind of incorporates everything. You won't see something that difficult on the test, but I could pick bits and pieces of this. You know, it probably won't be a little bit of everything, but it could be close. So expect to see something similar, when we move to vectors, it'll be that much easier now that we've practiced it here.